Wow, fantastic to see everyone. We're really, really thrilled to have you all out here tonight. It's a big night for us, leading up to a big few days at Google Next. Infrastructure is foundational to everything that we do. We're going to be talking a lot about AI. We're going to be talking a lot about agents. In the end, it is the infrastructure that powers it all. And as a reminder, you all are getting to see this before literally anyone else, so please do keep it under wraps until tomorrow. Okay, so I'd like to actually start with Google's mission. It's actually always, I've been at Google 16 years now, just about in a month. And the mission has sincerely always been inspiring to me. Right? Organize the world's information and make it universally accessible and useful. And I think it's a timeless mission. And actually realizing this mission required building an infrastructure that hadn't been invented before. Right? So looking back 25 years ago, and we won't go through the whole history lesson, but the way that people built infrastructure 25 years ago didn't support this mission, didn't support web search. And credit to the founders, the first employees of the company, Larry, Sergey, and others, they realized that it took significant investments in infrastructure and the fundamentals of infrastructure to solve this problem, to solve web search. Today, 25 plus years later, solving this mission requires solving intelligence. So the challenge is bigger than ever. The opportunity is bigger than ever. And just like 25 years ago, the infrastructure required to solve for intelligence doesn't yet exist. We're in the process of defining it. I think we've made some really, really serious advances. Today, you're going to be learning about, I think, one really big step we're going to be taking toward that definition of the infrastructure, the future of infrastructure, that's going to be powering solving intelligence. This agentic era is placing unprecedented demand on infrastructure. This is not an AI-generated image. This is Clarksville, Tennessee. This is our data center there. This is what it takes to underpin our services today. Search, ads, YouTube, a dozen services that have more than 500 million daily active users run on this infrastructure, and actually, AI is embedded into every single one today. And powering all that is, of course, our in-house infrastructure. We're going to be talking about that more today. This AI stack we've developed over the last few years, custom-built to solve the biggest problems in generative AI. At Google, we actually have a unique opportunity to really solve the problem end-to-end, vertically integrated. We don't just insert at one layer of the stack. We get to go after the entire problem. Starts with energy, one of the biggest constraints. We take this very seriously. The responsibility, the challenges very, very seriously. Right? Scaling out to solve the needs of the planet, actually for 25 years or more, but even more so today, massive challenge, massive opportunity, empowering it. Right? And we're doing fundamental work in scaling this out and scaling it out in a responsible way. From there are data centers, the lands, the enclosures, the buildings you saw, the cooling, the mechanicals, right, that house all of our infrastructure. Inside these buildings, the racks, the hardware, the servers, the storage, the networking, the TPUs, the GPUs that run, next layer up, our software. And this is what actually makes it all come together. Right? And without the software, the hardware actually isn't going to do very much for you. From there, and what's really changed over the last several years, are our foundational models. Gemini 3, state-of-the-art, all running on our in-house designed and built infrastructure. Right? And then these models, in turn, power all of our services. Search, ads, YouTube, photos, Gmail, and more. But they also power the cloud. Right? Thousands of enterprises rely on Gemini for their day-to-day. So zooming in, we call these bottom 4 layers the infrastructure stack. And if you actually look across the 6, if you were to take any one and try to design it in isolation, what you would do is you'd probably have to wind up with a least common denominator. What we can do is we can make sure that nothing is lost in the seams. As you move from one layer of the stack, we ensure that everything is integrated end-to-end for the highest levels of efficiency. the highest levels of reliability, and the highest layers of security. So now let's focus on the hardware. This is what we're going to focus on a little bit today. We've been at the hardware that powers this AI infrastructure for more than a decade. We kicked off our own custom silicon for supporting AI, our tensor processing units, or TPUs, in 2013. We realized that meeting the needs of the moment, meeting the needs of the future, in terms of the services that would come, would require a hardware architecture that didn't exist. And that's why we invented the tensor processing unit. And then generation after generation, TPU v1 in 2015, TPU v2 in 2018, we innovated. We added new functionality that actually presages what accelerated ML computing looks like today across industry. Things like liquid cooling, things like custom numerics, things like a custom network that connects hundreds, thousands of chips together in one supercomputer. The rate of innovation increased. We went from, let's say, 3 years between V1 and V2 to a couple of years to then an annual cadence. Last year, we introduced Ironwood here at Next, the most powerful TPU supercomputer we had to date. Okay, so then that begs the question. How do we follow up in 26? Right. Ironwood really actually has changed the world. It's running now, it's at massive scale, it's being built out across the planet. We're running on it at Google, DeepMind is running on it, all of our services, but many, many, many across the world in Google Cloud are running on Ironwood. So for 2026, I'm very, very proud to introduce our 8th generation of TPUs. Now, we're very literal here at Google, and what you'll notice here is there's a single S. I think there's a single S. TPUs. We're not introducing our 8th generation TPU. We're introducing our 8th generation TPUs. For the first time, 2 custom-built TPUs, 8T and 8I, and really designed from the ground up to meet the needs of the moment. TPU 8T, T for training. It's the powerhouse. It's the largest scale. TPU 8I, really built for inference. It's there for the agentic era. It's there for the lowest latency, for really delivering the content as quickly as possible to users across the planet. So let's look at some of the details here. TPU 8T. Roughly the same number of chips per pod, but 9,600 of them really interconnected with a custom ICI interconnect. 3 times, nearly 3 times the floating point power per TPU pod relative to just the last generation. Twice the network bandwidth in the scale out. 4 times the network bandwidth for scale up. We look across the TPU 8i, the reasoning engine. We've quadrupled or more the size of the pod. Now 1,152 chips, all coordinating together on the largest scale models running the most powerful agents, swarming together in near real time. 10 times the floating point 8 exaflops per pod. Right. And the HBM capacity, 7 times larger with the same bidirectional scale up. Now, what to me is the most amazing thing is this is just 1 year. 2x, 4x, 8x, 10x, all in 1 year. The rate of progress, the rate of advancement is just stunning. The way we like to think about it is that each of these years now open up a whole new set of use cases. With the capabilities of these chips, now all of our engineers, many of your engineers across the world get to think different. Things that might have previously seemed impossible, now we can go after. We open up a whole new world of capabilities and use cases and services, whether it's search, ads, YouTube, or your favorite service. What can they do with this much more computing power just a year later? So 8T, 8I, the other thing I'll note here is that these chips were both custom designed from the ground up for training and inference separately. These are not simple derivatives of one another. The specs, the capabilities, the connectivity, all different because they're specialized for the individual needs. So if you need the powerhouse training, you have 8T. If you need the lightning-fast inference, you have 8I. These TPUs are going to continue to power Gemini, but beyond, right? The models, yes, but increasingly what we see is that through services like Gemini Enterprise, we're literally changing how enterprises work. Healthcare, scientific breakthroughs, the rate at which these are accelerating is just truly astounding. In other words, we're getting to a place now where 10 years of research might take place in a single year. And how far we're able to advance is really determined by our computation power underneath. Okay, so it's a real pleasure to have shared with you our 8th generation TPUs. These have been in the making for 2 years, actually, at this point. They're going to be generally available later this year. I also want to really take this opportunity to actually thank the literally thousands of people, engineers and more, across Google who for these couple of years have really worked super hard to deliver both of these 2 chips. And I'll note also actually what's particularly gratifying to me is that we realized 2 years ago that 1 chip a year wouldn't be enough. This is our first shot at actually going with 2 super high-powered specialized chips, and the team has really delivered. So with that, I'm going to ask Ben and David to come back on stage, and we'll have a conversation around this. Thank you very much.
Hey, Amin.
Welcome back.
Good to see you.
Thanks a lot.
So, 2 chips.
2 chips.
2 chips,
Yeah.
1 year.
Twice the fun.
You've been busy.
It has been a busy year, a fun year.
We know you like history, so can we walk back to early TPU days?
We also like history.
Yeah.
I want to go to 2013 because you started doing custom silicon back then, the better part of a decade before the great AI arms race that we are in right now.
Yeah.
What is
4 years before the Transformer paper.
Yes.
Yep.
What is the origin story of why Google decided to do this?
Yeah, so, and actually the amazing thing is in 2013, if you were to transport yourself back to 2013, conventional wisdom, all the wise, smart engineers would say, custom silicon, bad idea. CPUs, they're getting faster all the time, just wait for them to get faster. But what we realized is that one of the grand challenges that we were going after at Google was translation, language translation. And this remains a grand challenge. We've gotten a lot better at it, actually, thanks to TPUs and, of course, all the models on top of it. But what we realized is that if you wanted to do things like translate from one language to another, one thing that you had to do was voice recognition. Right? You didn't want to just necessarily do the text. You wanted to actually understand what someone was saying, build the Star Trek Universal Translator. Voice recognition is incredibly computationally expensive, and it's also really repetitive. There's a lot of matrix multiplication. What we realized is if we try to do those matrix multiplies on a CPU, general purpose compute, we would actually have to go build 2 or 3 additional complete Googles if we wanted every Google user to interact via voice for 30 seconds a day. Now, we were a big company even in 2013. We had a lot of infrastructure. But tripling our infrastructure for this one use case, it wasn't affordable.
Yeah, I think Jeff Dean's quote on this was, we realized we needed another Google. Or maybe it was more, we needed 2 more Googles.
A couple more Googles. It was going to take a couple more Googles. And yet what we realized is that we could do it 100 times more efficiently with custom silicon. And there, the math stands up. Like, you could wait a long time for the CPUs to get 100 times more efficient. Normally, you'd say, just wait a few years, the CPUs will get there. 100x, you'd be waiting a long, long time, especially since we were seeing actually that the trend in CPU, certainly core performance improvements, was slowing down back then. And so it made sense. It was, even in 2013, I want to say, it was a controversial decision.
And in 2013, TPU v1 is very reasonable to call it an ASIC. TPU v8, not an ASIC. Where along that journey would you sort of characterize the change?
You know, and yeah, yes, TPU v1 was an ASIC. And I think that Google was not a hardware company. I don't know if we're a hardware company now or not. But we were definitely not a hardware company in 2013. And so it's been a progression. And it's been a progression in expanding our own capabilities, where year after year after year, we saw, OK, maybe we need to add this feature. Maybe we need to consider liquid cooling. Maybe we need to consider custom network interconnect, et cetera. So it really hasn't been here's a transition point from ASIC to not ASIC. We've taken on more and more, and now to the point where we're producing 2 chips a year. More and more capabilities because that's what was demanded. That's what was needed in order to make these products successful.
How did you guys embark on this journey? You obviously it was realizing you needed another Google, but most other tech companies buy this stuff. They don't decide, oh, actually, we're going to make our own chips, we're going to make our own data centers, we're going to make our own racks, we're going to generate our own power.
And this is something deeply embedded in the Google culture, and it's something that deeply resonated with me as well when I joined. And I think, again, I do want to give Larry and Sergey credit. There's this healthy regard for the impossible. And I think that if you think about it, I mean, the story I like is Google Maps. Who would have thought that it would make sense to fly your own airplanes and drive your own cars, mapping the planet? To first order, you'd think that doesn't make sense. And yet, it made sense. And so the willing to actually say the impossible actually might make sense. I think that we actually have a rich tradition of being willing to bet on things that very well might fail. Now, we celebrate TPUs. I think we should. But there have been a number of other things that we've done, we won't name those, that didn't succeed.
We know. We made about 10 hours of the history of
and that's,
Google.
And that's OK. And so I think the great thing about the culture is that there are people who have that insight, that passion, that willingness to go after it. We enable them to do it. And it's not that they get punished or the career gets hurt if they don't succeed. Right? You learn something. And by the way, most of the time, we actually make our existing products or some other product better through the failure. Right? Because we learn something through the process of failing. So I think it really is the culture of being willing to take a big bet. And initial investment was small. I probably 30, 40 people. This TPU V1, right? And maybe, again, don't quote me on this, but tens of millions of dollars, low tens of millions of dollars.
I think it was big and controversial at the time.
It was big and controversial at the time, but you know what? The cost of failure was also low. And the cost of success, apparently pretty significant.
From the acquired lens, I think one of the things that is the most interesting about Google in AI is the fact that it is a frontier model, a scaled infrastructure cloud, and a leading edge AI chip company all under one roof. And intuitively, it makes sense that those things should have advantages to have them in one company. I mean, no one else has quite that stew that Google has. What are some very concrete examples of how those teams kind of work together to take advantage of that integration?
I think number one, I mean, these TPUs would not have been possible in the early days without deep collaboration with the services. For example, language translation, voice recognition. I mean, the first TPU was essentially built as a application, literally an application-specific, single application-specific integrated circuit. Right? And so if you're going to build a piece of hardware for one application, there better be deep, deep collaboration between them. In the middle generations, and still today, these TPUs were used for recommender systems for our ads serving infrastructure. Deep, deep collaboration. What do you need? Where are the bottlenecks? How could we make the hardware better fit for your service use case? What software stack do we build to support you? And of course, most recently, I think it's fair to say that these TPUs wouldn't exist without the deep collaboration with DeepMind. In other words, being able to predict the future 2 and 3 years out really requires that incredible shoulder-to-shoulder partnership with the DeepMind team, with the research team, that is going to be putting these into use.
What's an example with TPU V8 where you made a proposal to DeepMind and they said, actually, can you make it do this instead?
Yeah, so one of the things that we're probably most proud of, and we didn't talk about it much here, but it's going to come out, so I'm going to, again, give you all a super early preview, is TPU8i really drives down latency. And one of the things that we've had to realize is that the way that we were connecting the chips together, the network topology is a little bit low level, but I'll keep it hopefully understandable. The way that our default way of connecting them together didn't support latency, it supported throughput. It supported bandwidth. It was really good at getting large amounts of data through. But what you really care about in the age of agents is the latency, the minimum time it takes to get the data through. And so we actually collaborated together to build a specific network topology that connects these chips together, a really novel one. Actually, it's called BoardFly, that dramatically reduces the diameter of the network. So the distance between any two chips goes way down. And this is really sincerely the only kind of insight that if you were just building the chips, we just say, well, let's make the last generation faster. Okay, so that's a good thing to do, last generation faster. But when you actually change the architecture based on insight of what the service needs, that's the game changer.
Because 2 years ago, I am just spitballing here, I imagine you probably started design of this somewhere in the neighborhood of 2 years ago.
Yes.
No one was talking about AI agents. So it's not like you could design specific hardware.
Yeah, it's hard to remember now, but only 2 years ago, nobody was talking about AI.
And so this is the awesome thing. 2 years ago, we were internally talking about AI agents. And we were talking about the reinforcement learning in real time in response to requests. It wasn't the dominant workload, right? And you could also say, well, there were competing requirements, et cetera, but what we could see is that where this was going to wind up, really good chance that agents and low latency in particular were going to be there. We have to take some bets. Right? But because, we have thousands of people, thousands of researchers working to predict the future. If many of them, and these are the leading minds, sincerely, I know I'm a little biased, but the DeepMind team, leading minds on the planet, among the leading minds, there are others, of course, other groups. If a number of them are telling you, this is where things are going in a couple of years' time, you're taking notes.
Yeah, when you spoke a little bit about it already, but let's talk some more about the two chips. On the one hand, it's twice the work. That's a huge strategic decision.
Yeah.
Probably that when you made it, the compute market and demand was still very much training first.
Yeah.
How did you guys think about making that investment?
We had actually, I am a fan of history, and I think that one of the biggest reasons to study history is that it gives you a leg up in being able to predict the future. And so we actually had, by that point, a significant amount of Google history behind us. And if you think about web search, the number one problem in, let's say, 2000 was building the web index.
Yeah.
Training a model. We didn't call it that, but building a web index.
The large upfront one-time work.
And exactly, you all might remember, maybe you all remember, maybe some of you don't. There was a time when you said, the new web search index is now available.
Yeah,
it happened every few months.
Google used to update every couple months,
and then weeks.
right?
And in the footer, it would list the number of indexed pages.
Exactly,
Yeah,
the new index with the number of parameters, I think you meant. but yes, you're right, it was a number of web pages. So the new web index is available. We worked hard for 2 months. We threw tens of thousands of servers, which was a lot back then, tens of thousands of servers crawling the internet, building this index. Now, where's the value of the index? The value of the index is serving it. By, let's say, 2005, for sure 2010, but let's say 2005, what was the dominant thing we did on our infrastructure? We served the index. And we could see that things are on everything that was happening 25 years ago is happening, but it's happening on much compressed timescales. So we knew, yes, training, that's the dominant workload, but the value is going to come from serving the model. Of course, all the hard work is going to go into building the model in a lot of ways, but serving it is where the value is created for Gemini Enterprise and search and ads and YouTube and so much else. Right? And so we could make a bet that and we were starting to see the exponential take off for serving. And if you carry it forward 2-3 years, okay, now, 2024, this is the year where we're going to go after 2 chips.
So it's funny, I'm curious how you think about the use cases for TPUs and who it's for, because we're all sitting here at Google Cloud Next. This seems like it could just as easily be at I/O. This is an underpinning of Google across every group. How do you think about where TPU is across the Google portfolio?
My team, we're fortunate in that we actually sit in cloud and we sit in Google as a whole. So we have a dual role. And we take this role and sort of responsibility as a privilege, honestly. So we power Google, we power all of our consumer services, we power cloud, and of course all our enterprise services. So use cases, again, I think that it's fair to say that Google Search has changed more fundamentally in the last 2 years than the previous 25. Right? If you look at AI mode, AI overviews, and actually,
practically every search I run these days has AI mode, which
yeah,
I think
Overviews.
about,
AI
or
overviews.
sorry, AI overviews.
Right.
Yeah, yeah. And I think about just like, wow, what is the cost that is going into that?
and we're very proud of the efficiency work that we've done to actually make it possible to be able to power that into essentially every Google search, right? And that the
Even
TPUs
non-monetizable ones.
Not exactly. For us, and this is the great thing about how we're set up, is that Search's goal as a business unit, and I love this about the company, is not to make money. It's to produce the highest quality, most engaging results. There's a separate organization, a fantastic one with the smartest people as well, that generates the ads. But Search's job is, like, whether it's monetizable or not material, produce the best results. And they're doing so with TPUs. Now, on the flip side, you'll hear this example tomorrow. We covered it actually at a session today, so I think I can mention it here. Citadel, leading securities trading company in the world, they use TPUs. Are they doing it for frontier model training or model serving? No. But actually using TPUs, they've made their trading systems 2 to 4 times more efficient. They've reduced cost 30%. Because so it turns out that while it's a specialized architecture, these TPUs over 8 generations have become more and more general purpose, taking on a number of mathematically intense use cases.
Wow.
As you solve some of the bottlenecks in the 2 variants of this chip, and you're starting to feel like, wow, this is an unbelievably high performance piece of silicon, where are the remaining bottlenecks? Where will the issues start to show up elsewhere in the chain?
So one of the big ones for us is reliability. So when we talk about our systems, I think at this point, it's fair to say it's not just 9,600 chips that are working on a problem. In many cases, it's tens of thousands, and dare I say more, that are all coordinating together at literally nanosecond scale. What this means is that if any one chip fails, the computation stops. I mean, literally, there's like a nervous system where everyone does a bit of computation, and then they exchange information with everyone else. I mean, I'm simplifying. You all know the
This is in
details.
training.
In training, but also in inference. The scale is smaller in inference, to be fair. But we still run on perhaps hundreds of chips.
Yeah.
What this means is that if any one of them stop, that nervous system stops distributing the information. The whole computation comes to a halt. Now,
Still, I assume this was a solved problem.
that's actually a primary problem for us and for essentially the entire industry. So what we are proud of is these chips, they're wonders of nature. And you all are very knowledgeable here, but they're using the most advanced physics, lithography, materials, and these are the biggest chips, essentially to first order, and you can see one chip is a different size than the other, but these are essentially the biggest chips that you can buy. What this means is they fail.
Yeah.
Okay? And ours fails, other people's fails, they fail. There's just inherent failure. And they fail more than other chips, and what that means is if you say, okay, they're reliable, but if there are 100,000 of these who are going after a piece of computation, what's the chance that one of them fails? Well, you do the math, and it turns out pretty good. So, several times a day, I won't say whether, but within that order, several times a day, at least one chip is going to fail. Now, how quickly do you detect that failure? What's the needle in the haystack? How quickly do you reconfigure the system to start running again? If you imagine that it takes, let's say you have a failure every hour. If it takes you an hour to find the problem and fix it, you have zero throughput. Right? By the time that you start up again, you're failing something else. And if a human being has to get involved in that failure detection and diagnosis, there's a rule: human gets in the loop, minimum 30 minutes. Smartest, most knowledgeable person, that's just what it's going to take, minimum. And it could easily go to hours. So actually, our work in driving this reliability to massive levels, we are able to deliver on 10,000 chips more than 97% good put. What that means is actually how much forward progress we're making, not just, okay, what's the theoretical flops if everything were going perfect.
You said good put?
Good put.
Never heard that before.
Yeah, so it's not just throughput, because you can
yeah.
be doing a bunch of computation and not making any progress. You could be spinning your wheels. Good put, you're making progress. 97% means 100% is no failure, everything's working perfect. 97% means that you're finding those issues when they happen, and you're recovering from them super quickly. And so reliability, key issue, and I'll just throw one more in. The worst ones are not fail stop, but when you have what we call silent data corruption, when you have one chip that silently gets the computation wrong every once in a while. Those are the worst. Because it's like the genius who can get it right almost all the time. Well, if you make one error an hour, actually that's a big problem because these chips are all talking to one another. One chip's error goes to everybody. So the problem of making these things run in production at scale, massively challenging.
It becomes much less a narrow chip development problem and this like very broad systems engineering thing.
Exactly. End to end, and there's literally hundreds of issues that have to be discovered and fixed. Each of them pretty challenging until you get to that point where you can deliver this massive reliability at scale.
Well, maybe as we wrap up here, we're here at Cloud Next, have this incredible announcement, 2 chips today.
Tomorrow.
5 a.m.
5 a.m. tomorrow. Sorry. Tomorrow. Incredible announcement tomorrow. What can you tell us about the future, looking a few years out? I'm sure your roadmaps for many generations are already coming together.
Yeah, so the future, I think, is one of really re-examining the conventional wisdom. So like I think one of the things I'll say, though, is with agentic computing, there'll be 2 parts to this. CPUs are going to make a comeback. That's a prediction I'll make here today. In other words, there's a lot of general purpose compute that is involved in running these agents. They're orchestrating all this inference that is taking place. They're creating sandboxes, virtual machines, to build code, run it, check the results, and then find the next set of outputs. So general purpose compute is going to make a comeback, so that's one side. The other side is the age of specialization is going to continue. So I wouldn't be surprised if 2 chips here, we're going to find additional workloads that might need their own chip. Whether it's us, I'm going to make a prediction for industry, not for Google. But at a time when general purpose CPUs are really only improving in performance 5% a year, normalize the cost, you have to specialize. If you're really going to go after these brand new workloads, so 2 chips might become more, maybe they're not TPUs, maybe they're going after a different workload. But the age of specialization will be upon us in the future.
Well, I mean, that is a great place to leave this. Yeah. Thank you so much.
Yep, thank you. It's a lot of fun.
Appreciate it.